First of all, from the information I provide in this podcast, you cannot make an atomic bomb. That should be fairly obvious. It took some of the world's greatest scientists many years to develop the first nuclear weapon. I'm not one of the greatest scientists, merely an A-level physics teacher, and so cannot build a nuclear weapon, nor would I try. However, the British A-level qualification requires that you know the basic principles in making the most destructive weapon ever devised. So here goes. As we discussed during the binding energy per nucleon podcast, uranium splits because it forms two more stable nuclei with a higher binding energy. The splitting process releases energy into the surroundings. The point we will discuss here is why it splits and how we can make it so that it keeps on splitting more and more uranium nuclei without outside intervention. First things first, how do we split the atom? This is a fairly easy principle to grasp if you have ever played snooker or pool. Imagine the uranium nucleus as a collection of red balls arranged in a V at the start of the game. In order to split these reds up, you need to launch the white ball into them with sufficient speed. Too slow, and the white ball will just gently nudge the red balls. Too fast, and the white ball will bounce off the pack without doing much to them at all. The neutron is the white ball in our analogy, and the speed it is travelling at is the thermal region. That is why the neutron is called a thermal neutron. This is where our analogy ends. In order to split one uranium nucleus, you need the neutron to be absorbed by the nucleus of uranium. This will only happen if the speed of the neutron is just right. The neutron is absorbed by the uranium-235 nucleus, and it makes it more unstable. In fact, the uranium-235 nucleus, now a uranium-236 nucleus, becomes so unstable that it splits in two. It will only work for a uranium-235 nucleus, not the much more common uranium-238 nucleus. Once the U-235 is split in two, you find that the reaction has also caused the release of three neutrons of a very fast speed. But if they're slowed down, or if you set the thing up right, those three neutrons can go on to split three further uranium-235 nuclei. If they're slowed down, these neutrons are also thermal neutrons. This release of three further thermal neutrons means that once we have started the nuclear reaction, if we set up the conditions just right, we can leave it to keep going itself. This is called a self-sustaining nuclear reaction, or a chain reaction. But setting up this situation requires a little more detail. You see, it isn't just splitting one nucleus of uranium-235 that makes a nuclear bomb work. You have to split billions of them in a short space of time. That can't be done by you firing neutrons at individual nuclei. It needs to be done by getting these newly produced neutrons to go on to split other nuclei of uranium and form a chain reaction. The key to doing this is the concept of critical mass. The three neutrons produced in the fission event can be the right speed to split further uranium nuclei. However, they may not reach the uranium nuclei in time, or they might not be at right speed. Even at a very pure, natural sample of uranium-235, the spaces between nuclei are far too big for the neutrons to hit them. You need to make your fissile material close together, so that the neutrons produced in initial fission can cause further fission. To do this, you need to purify up to weapons grade, which is a very high concentration of uranium-235. Once you have a reaction so that one neutron produces one further neutron, you have a critical reaction. The reaction is self-sustaining. When you have this mass of uranium-235 together, it is therefore called the critical mass. You have gathered together enough fissile material in close enough proximity so that the neutrons produced by one fission of uranium-235 can be used to instigate a further fission in another nearby uranium. Once these conditions have been met, you can have a runaway chain reaction, a nuclear explosion on your hands. The same principle applies to a nuclear reactor, but here we have more materials in place to keep this reaction off the boil and not become uncontrolled. We also have much lower concentrations of uranium-235.